the dominoes effect goes as follows. For a pair k not equal to L and the pair k, L is not n, 1, let's look at the following iterated Lie bracket. E sub k1, comma, the Lie bracket of E sub in, comma, E sub nl. We want to show that this guy is equal to E sub kl. From intuition, this should be true because of the naive thought that the tail 1 cancels with head 1, the tail n cancels with head n, and all that is left are k and l. But we have to check this more rigorously. And I tell you, at some point, we have to use that k, l is not equal to n, 1. So let us just break down this iterated Lie bracket. This is equal to E sub k1, comma, by definition this guy is E sub in times E sub nl minus E sub nl times E sub 1n. So I should make L distinguishable from 1. And this product can be just reduced to E sub 1L. But we do not know whether L is equal to 1 or not. We only know that the pair KL is not equal to the pair n, 1. But let us continue. By linearity, this can be further broken down into the Lie bracket of E sub k1, comma, E sub 1L minus the Lie bracket of E sub k1, comma, E sub nl times E sub 1n. And we'll look at these two parts separately. The first part is easy. This part is equal to E sub k1 times E sub 1L minus E sub 1L times E sub k1. And because we assumed that k is not equal to L, this part must be equal to 0. So this first guy will just be equal to E sub kl, because the product of these two will be E sub kl. And now let's look at the second one. The second guy, if you just look at this product will be equal to the Cronach delta of L and 1 times E sub nn. If L is equal to 1, then we are good, we get E sub nn. If L is not equal to 1, then we'll get 0 for this. And by the definition of Lie bracket, this is equal to delta sub L1 times E sub k1 times E sub nn minus delta sub L1 times E sub nn times E sub k1. And we claim that this guy must be equal to 0 because of assumption that kl is not equal to n1. Do you see why? I'll let you think about it for a while, and I will tell the answer anyway later. This is because if L is equal to 1, then although those two Kronecker deltas are equal to 1, those two guys are both equal to 0. Then since in this case K must not be equal to N, and N is greater or equal to 2. Because N is greater or equal to 2, this product must be equal to 0. Since the only case when this could be not 0 is that N must be equal to 1. But here we assumed at the very beginning that we are only discussing the simplicity of SLNC when N is greater or equal to 2. So this guy will be equal to 0. And because K is not equal to N, this guy must also vanish. So we'll get 0 minus 0, which is 0. That is the first case. Now if L is not equal to 1, then trivially those two terms will vanish. In any case, we get that the second thing is equal to 0. And now, because A is an ideal in the Lie algebra, this equation shows that E sub KL must be in A, since E sub 1n is. And so far, we have proved that almost all E sub KLs for K not equal to A are in A. It only remains to deal with the case when E sub KL is equal to n, 1. Let's call this case A. Now let us look at the other case, the case B. Suppose K, L is precisely n, 1. Notice that n is greater or equal to 2 by our assumption at the beginning. K is already different from L in this case. And we want to prove that E sub n1 is in A. And to this end, we will need another Lie bracket manipulation. This time, we're going to look at E sub n, n minus 1, the Lie bracket E sub n minus 1, n, E sub n1. And we hope this, if you cancel out the tail with the head, you will get E sub n, 1 in the end. Let's see. Maybe this does not lead to what we want. Simply using the definition, this is equal to, for this part, you will get E sub n minus 1, n times E sub n1 minus E sub n1 times E sub n minus 1, n. Clearly, this part will be just E sub n minus 1, 1. So let me just rewrite this. And now, using the linearity, we'll break down this Lie bracket. For the first part, this by definition is equal to the first times the second minus the second times the first minus the second guy. This part is 0 because n is greater or equal to 2. So this doesn't match, which forces the product to be equal to 0. And this part will just be equal to e sub n comma 1. And now let's look at this complicated guy. It is equal to e sub n comma n minus 1 times e sub n1 times e sub n minus 1 comma n minus the other way, product. This term will vanish because here n is not equal to n minus 1. So product of those two matrices is already 0. So this guy is equal to 0. In the end, we are getting e sub n1 plus e sub n1 times e sub n minus 1 comma n times e sub n comma n minus 1. And you can further combine those two matrices into e sub n minus 1 comma n minus 1. Okay, good. We have simplified this a lot. And remember, our goal is to prove this guy is in A. So we only need to deal with this term. There will be two cases to consider. If n here is strictly greater than 2, then n minus 1 is not equal to 1. So this guy will vanish in that case. We will only get e sub n comma 1. For the second case, if n is equal to 2, then n minus 1 will be equal to 1. So we get twice of e sub n comma 1, which is in this case just twice of e sub 2 comma 1. However, you should have already noticed that this guy lives in A because A is an ideal, and we have already proved in our part A. Remember, in our part A, we have already proved that if k is not equal to L and k comma L is not equal to n comma 1, then E sub KL is in the ideal A. And in particular, for this matrix E sub n minus 1 comma n, n minus 1 comma n satisfies this that it is not equal to n comma 1. So this is already in A by the case A. So since this A is an ideal, we have this iterated Lie bracket is in A. And we proved in the end that either E sub n comma 1 is directly in A or twice of it is in A. However, as an ideal in the algebra, it is already a complex linear space. So in this second case, since an ideal in G equal to SLNC is always a complex linear space, that twice of an element in A implies that this element itself is in A. Here we also use the fact that C is a field of characteristic not equal to 2. It has characteristic 0. So 2 is not 0, so that you can take inverse to get E sub n, 1 is in A. Hence, we have E sub n1 is in A. Now, if we combine the results of part A and part B, I should say cases A and B, we get E sub KL is in A whenever K is not equal to L. Notice here we have already used the hypothesis that n is greater or equal to 2. Okay, at this point, let me remind you first what we have achieved so far. So far, we have proved for any k not equal to L, we have E sub KL in this ideal A. We have proved this by assuming our claim. We haven't proved this claim yet, but assuming this claim, we proved that E sub ij is in this ideal for any I not equal to j. And our final goal is to prove that A is equal to G. But our discussion at the beginning, it suffices to show that E sub ii minus E sub jj is in A for any I not equal to j. Because once this is proved, then H is also contained in A. So A contains G, which means A is equal to G. But the proof that E sub I minus E sub jj is in A is really easy. This is because for k not equal to L, we can write E sub kk minus E sub ll as the Lie bracket of E sub kl, comma E sub lk. And this is in A because both of those two things have already been proved to be in A. This is just what we have done so far, with a lot of effort. We proved that when k is not equal to L, then E sub KL is in A. So both of those two terms are in A by the cases A and B above. And therefore, H is contained in the ideal A. So G, which has the decomposition as the direct sum of H, and the direct sum of C times E sub ij's, where I is not equal to J, is also contained in A, which forces A to be equal to G. The Lie algebra G equal to SLNC. This finishes the proof that if we have E sub 1n is in A, then A must be equal to the whole space G. As a proof that when E sub n1 is in A, we have A is equal to G will be similar. Let me still write this down. Similarly, if E sub n1 is in A, we can prove that A is also equal to G. Hence, It suffices to prove the claim. Let me copy the claim down in here.